colleagues. Good afternoon, Doc. My name is Magdazi. Um, this afternoon, I'm presenting on the optimal control model for the spatial spread of COVID-19, an interacting fluid flow approach. And I'm supervised by Dr. Stephen Edward Moore.
This is not your support. This is not your thesis work. This is a presentation
Yes,
seminar.
please, Doc. Okay, seminar. Okay, Doc. So my seminar presentation runs from introduction and motivation to conclusion. These are some of the keywords that will be used in this presentation: COVID-19, spatial epidemic modeling, interacting fluid flow, partial differential equations, hyperbolic systems, optimal control, vaccination and treatment strategies, the WENO scheme, which is the weighted essential non-oscillatory scheme, and then the Runge-Kutta method, and then sensitivity analysis. We start with a background. COVID-19, which came around 2019, so it has the name COVID-19. It's an infectious disease, and its spread is very fast. But then mathematicians have been able to explain using mathematical tools, but then the tools they use are usually the ordinary differential equations. But these ordinary differential equations works nicely because it looks at short time scales, which is not adequate for especially heterogeneous outbreaks. So when we consider the COVID-19 outbreak, it's clear that the question of where does the outbreak intensify, its concentration, and how fast the infection spread is not really captured in the case of the ordinary differential equations. And so it becomes necessary that mathematicians have a different look at how the COVID-19 spread and then how fast it spreads. Before that, we will consider a classical SIR model to show what the ordinary differential equation would be. So this is the flow chart for a simple classical SIR model, with the uppercase lambda being the recruitment rate into the susceptible population, and then the force of infection is beta SI, and then the natural death rate for susceptible population is mu. Natural death rate for the infected population is also mu, and then the disease-induced death rate is the VAFI, and then the rate of recovery from the infectious compartment to the recovery compartment is the gamma. Now, when we write down the equations from the flowchart, we get equations 1 to 3 with these initial conditions and invariance region. The motivation is that once we are able to find the reproduction number for the SIR model, then we can easily get another reproduction number from the spatial model. So in this case, we go ahead to find a reproduction number for the SIR model using the next generation matrix. And then we know that for next generation matrix, we will need the vectors F and V, matrix, F and V, and then take the product to find the spectral radius. So we end up having the reproduction number of the SIR model to be this. So once we know that the SIR model would have a reproduction number of this, then we can try and then improve upon this reproduction number to really understand how fast the disease spread, and then the concentration levels. So for the spatial mode model formulation, we would use the continuity equation or the transport equation. And then the first term here, this shows the population density. And then this shows the velocity field. And then this gives us the source or sink. The uppercase x we see is dependent on the lowercase x, which is in the horizontal direction, and then lowercase y, which is in the vertical direction. The spatial model formulation is based on the following assumptions: that there is an inviscid flow, that the susceptible and infected populations do not have any internal friction, and then the whole population is considered as one. We are not looking at the individuals in the population and how they move. We consider the whole, for instance, the susceptible population as one thing, and then the infected population too as one thing, so that we don't consider the individuals in the population. And also, we have a closed domain that there is no entry or exit of people in the either susceptible or the infected population. And so when we go forward, we look at the work by Cheng and Wang, and then they actually used this transport equation on an SIR model, but then they didn't include some terms for the infected, the rates of death of disease induced in the infection compartment. And so this paper includes it, and then deduce these three using the transport equation. So just like we saw in the transport equation showed, all we have here gives us the source terms, and then this one gives us the velocity, and then this gives us the concentration of the susceptible population. The same for the infected population. The source is the right hand side, and then the velocity is the K sub I, and then the concentration is the I, dependent on time and in space. And then the recovery compartment or recovery population is also having this to be the source or sink, the source, sorry. But then the recovery do not have velocity because they have recovered and they are not going back to the susceptible compartment. And this gives us the initial boundary conditions for the transport equation. Now the K sub S that we saw earlier on is also dependent on the U sub S and then V sub S. These are all for the horizontal and then the vertical direction, which will also depend on space and time for both the susceptible compartment and then the infected compartment. Now we have considered only the transport of the population from either the susceptible compartment to the infected compartment or from the infected compartment to the recovery compartment. But then we haven't looked at the velocity. And so in order to model the velocity of these compartments, we use the Euler equation, which is coming from the Navier-Stokes equation. But with the Navier-Stokes equation, there is an inclusion of the flow, the viscosity of the fluid. But then with the Euler equation, we consider that the fluid doesn't have any internal friction, and so that term goes to zero. And so this is what we'll be left with for the Euler equation. And so S, as we know, is the concentration, Q is the velocity, Q sub S the velocity for the susceptible population, and then this term here is the pressure term. Now we go ahead to close this equation by close this equation by picking some constant K sub S for the susceptible compartment and then K sub I for the infected compartment. And once we have defined what these pressures are, then the spatial model is complete, and then we can put them together in this coupled form. So the first part we see here gives us the transport equation, and then with its velocity, which is the Euler equation. Now, when we are done with this, we try to write it in a compact form. And so we would multiply, we would expand what we have here, and then the susceptible concentration times this would give us that, and then this is with the whole of this will also give us that. And then we do same for the infected compartment. Now, when we add the transport equation and the velocity terms, we end up having this. So we multiply these equations with their various velocities, Q sub S and Q sub I. And then when we multiply these with their velocities and then add to our expanded velocity equations, then we are going to have these two, equation 14 and 15. So after adding these, we go ahead and then expand them in their component form. And in their component form, we would have the first term here representing the transport equation, and then the second term here representing the velocity in the x in the u sub s direction, the horizontal direction, and then we would have the third term also in the vertical direction. We do same for the infected concentration of infected population, and that also gives us the first to be the first equation to be the transport equation, and then we expand what we had for the velocity in the various directions. That's the vertical and then the horizontal direction. So in compact form, we see clearly that the term u here represents the independent terms, and then the m we see here is in the direction of x, the n we see here is also in the direction of y, and then this is our source term. But you realize that m here is a function of u, and so that's a composite function. And so if we want to split it up, then we would have to apply the chain rule, and then we differentiate m with respect to u, and then now go ahead to differentiate u with respect to x. So when we apply the chain rule, everything expands beautifully to this. Now, when we go back to what we were adding, we realize that when we come here, we realize that the first column we see here gives us our independent terms. The first term S, we see here, SUS, SVS, I, IUI, IVI, gives us the U terms here. And then the next terms in that column is also collected in N of U, and then that of M is also collected here. And then the source terms are also collected here. Now we go ahead to find the Jacobian of these in order to linearize. We want to check the nature of the system before we can then go ahead and then use a specific or a particular numerical scheme. Now, with respect to this system, we need to show whether it is either a hyperbolic, a parabolic, or elliptic. And then this would be possible only when we know the nature or the behavior of the eigenvalues. If it is positive eigenvalues, then we are thinking of hyperbolic. If after our calculations, we are getting the eigenvalues to be repeated, then we are thinking of parabolic. And then if it is a complex eigenvalues, then we are thinking of elliptic. And these will determine what kind of numerical scheme you should use. And so in forming the Jacobian, we need to first of all differentiate each term. For instance, I take the first term m us, and then so if I want to fill up the first row, first column of my Jacobian, then I'm going to take sus and then find its partial derivative with respect to x. And then I take the same sus and then do same with sus, take the same sus and then do same with svs. And then that fills up the first row of my Jacobian. And then I move on to the second term. For my second row, repeat same for these independent variables. I take my third susvs for my third row. I do same for this, and then that fills up my 6 by 6 matrix for the m or the x directional vector or matrix. And so when I finish, I do same for n of u with the same respect. Now these are the fluxes, so we would determine the nature with these two when we have really defined some constant for them. So for instance, if I take the first term, which is sus, and then the first term sus with respect to x, with respect to s will mean that I do not have any term in the numerator. With respect to the Jacobian derivation, we do not consider these two as separate terms. We consider them as one. And so there is no term here, making that there is no term in s alone in the numerator. And so our partial derivative goes to 0. But when we consider the second term here, which is sus, we realize that we end up having the partial derivative of sus with respect to the partial derivative of sus, and that is going to give us 1. And so we go through the same process for the rest of the terms, and then this is what we are going to get for our derivation. This is what we are going to get for our derivation for the m. And so when we move on to find the Jacobian for the n as well, we go through the same process and then we get b of u, which is the partial derivative of n with respect to u. Now, when we finish with this, we define some constants m and n, some constants m and n. And when we define these constants and then multiply them with a Jacobian in the x direction and a Jacobian in the y direction, we obtain this 6 by 6 matrix here. Now you realize clearly that these the matrix we have here is a block diagonal, meaning that we have this block, we have this block, we have this block too, and then we have that block. So this is a 3 by 3 block diagonal. So we expect that the eigenvalues would be on this diagonal. So we pick each block, and then when we go through the characteristic polynomial method, we end up having these eigenvalues. Now for the susceptible, we get lambda 1 to be mus plus nvs, but we have already said that k sub s from the pressure equation is positive. And so this lambda 1 or this eigenvalue is positive. When we check for eigenvalue 2, it is also positive. And that of eigenvalue 3 is also positive. And so for that block, the first block on the diagonal as shown is for the susceptible population. The block here is for the, and then the block down here is for the infected population. And so when we consider, we realize that, like I said earlier on, if we have positive eigenvalues, then we are thinking of a hyperbolic system. And once it's a hyperbolic system, we can go ahead and then use the Bueno scheme and Bueno numerical scheme. But before that, we need to check the stability of the system. And so in checking the stability, we expand our function U using the Taylor expansion. And then we ignore the higher order terms. And so we go ahead and then linearize. And then we know at equilibrium, we expect that in the direction with respect to t, with respect to time and space, will all be equal to 0. The system itself will be equal to 0. And so when we expand the x directional terms in using the Taylor expansion, we get these. We get this. And then in the y direction, we end up, it's approximately that, we end up getting this. So when we substitute into our compact form that we had, then the first term, which was for partial derivative of u with respect to time, is this. And then what we have here, it ends here. What we have here we have the first term to be this, and then the second term for m moves from this to that, and then the third term would be that, and then the source term will also be that. Then for us to check the equilibrium, we define the change in u to be, we redefine the terms here. So instead of delta u, we use u sub b for simplification. Now it means that we are going to evaluate the partials, the Jacobian matrix we had for the m at the equilibrium point. And then when we check here, our equilibrium point in this is S naught for the first, second, third, fourth, fifth, and sixth term because of no infection at equilibrium. It's a disease-free equilibrium point. And so we substitute into that, and then we end up having this to be our matrix in the x direction, and then this to be our matrix in the y direction. And now we go ahead and then take the Jacobian of the source term, which we haven't done. And so when we check the source terms for each and then take the Jacobian, we end up getting this matrix. Now, when we get this matrix, we go ahead and then evaluate it through at the equilibrium point. But at the equilibrium point, we expect our S naught that we had to be lambda over mu. Lambda over mu. And so when we substitute, our lambda over mu would be our S naught. Now, when we are done, we have already given and found these terms at the equilibrium, the A, B, and C. And so we go ahead and then find an answer, because this is a nonlinear PDE. And then nonlinear PDEs are very difficult to solve. So we start with a guess. So the answers we see here is just a guess, and then it is dependent on time, space directional x, and then space direction y. And so that's what we have here. We will go ahead and then differentiate this and substitute. So when we differentiate this, we end up getting, we differentiate what we have here with respect to time first, and it gives us that. We differentiate this again with respect to x, and then you realize that the eta t would go to 0, and then we'll be left with only ik, which is also here. And then when we differentiate the same answers with respect to y, we end up getting this. And so when we substitute back into our equation, we end up having this. It is clear that we can factorize out these terms. And so when we factorize out these terms, we end up having that the e exponent eta t plus IKS plus Ly cannot be 0. And so we expect that it is this portion of it which should be equal to 0. And that brings us to the finding of the eigenvalues so that we can tell whether the system is stable or not. And so going ahead, we would go through the same process. We go back to our A we had here, and then our B and then C. We go back and then we substitute we multiply with our eta I and then the ik and then the il, and then now we add everything and then equate to 0, and that brings us to this, and then that brings us to this. And so we see clearly that this is what we are going to get. But then we need to find the eigen values, and so we need to state the characteristic equation, and that would be eta I minus zeta star we had in the previous slide. And then when we finish, we go ahead and take the determinant of this. Now when we take the determinant, these are the terms we are going to get, and then simplifying these terms, we are going to get these eigenvalues. Now when we get these eigenvalues, we see clearly that the first eigenvalue is 0, and that is in a neutral mode, which means that the system is as it is. It doesn't go through any perturbation. Now, when we check the eta 2, 3, it is coming from the susceptible compartment. And then we see clearly that when there is any perturbation around this, around the equilibrium point, the susceptible population, the susceptible concentration would move away from the equilibrium point because the eigenvalues we are having is negative. But when we check the propagation of the infection, which is coming from the infectious department, that is for the eta 5 and 6, the eigenvalue 5 and 6, we realize clearly that we see this term is analogous to the reproduction number we had. And so we go ahead and then deduce that the stability of the system would strictly based on the the reproduction number we had from earlier on. And so when we factorize out this term, these terms here, we end up having this outside the bracket, and then we are going to have lambda beta all over mu times gamma plus var phi plus mu, which is actually our R naught, and then it would be minus 1. So this shows that our stability would still be assured that if we have R naught being greater than 1, then the disease will spread, and then when R naught is less than 1, then the disease will die out. And then this is a bidirectional wave speed because in the x and then the y direction. This would be the unit vectors in the x and then y direction. Now we go ahead to set up the numerical scheme using the weighted essentially non-oscillatory scheme. And this is based on the fact that our eigenvalues we had earlier on showed the system is a hyperbolic system. So for the Weno scheme, we will need lower order stencils. And then these stencils are just like we have the grid point xj, and then we go back, we have xj minus 1, and then we go back again, we have xj minus 2. We go forward and then we are getting xj plus 1. And so once we have fixed y, here, we expect to get these grids. Now for the reconstruction, we expect these candidates S naught, which is taking yk and then going back, and then we take yk minus 1 and go forward, and then take yk and then go forward. So it's like we have this is for a fixed xi. So for a fixed xi, we are going to have a yk, and then we go forward to have a yk plus 1. We go forward again to have a yk plus 2, and then we come back to have a yk minus 1. And so we move from yk to yk plus 2, which is this yk plus 1, yk plus 2, and then we can stand on yk and then go back to yk minus 1, yk minus 2, and then we can stand on yk minus 1 and then go to yk and then go to yk plus 1 here. So we go ahead and then find the nonlinear Wino weights, and the terms are omega 1 is actually the nonlinear Wino weights, and then alpha 1 are the unnormalized weights, then D sub L are the linear weights, beta 1 is the smoothness indicators, and epsilon should be positive so that it will not be divisible by 0, and P is a positive integer controlling the sensitivity to smoothness. Now this is our Weno reconstruction in the two-dimensional, which we see clearly that it is in the x direction. It is in the x direction and then in the y direction. After that, we go ahead to find the semi-discrete Weno reconstruction, and this is coming strictly from the finite difference method. This is coming from the finite difference method for the x direction and for the y direction, and this is our source step. So for the time discretization, we use the Brunsch-Kutter method, and then it is of the classical fourth order. So this is the first order, second order, third order, and then the fourth order. And then what we see here is simply ujn plus 1 sub jk minus this, which we have rewritten to get that. Now these terms are what we have its equivalent here. The next is, now we check for the optimal control. So it is with the fact that if we are considering the spread of the COVID-19 using the ordinary differential equation based SIR model, then in which direction are we going to apply what intervention, and then where are we going to apply what intervention? And so once we have been able to deduce that, we can actually find the direction and how the disease spread, then it is possible to now introduce interventions to stop the disease or to reduce the spread of the disease. And so for optimal control, we have the first optimal control would be for vaccination, which would be on the susceptible population, and then the treatment would be on the infected population. And so when we incorporate the interventions into our two-phase spatial model, then we are going to have the last term here catering for our first optimal control, and then our second term here for the infected being the optimal control. So we now get a new spatial system which includes the optimal control. Now I'll go ahead to find the reproduction number of this optimal control. And so for the reproduction number, we will first find the disease-free equilibrium, and then we know that we will not consider any infection at the disease-free equilibrium. And so we get the S naught for the controlled spatial model to be that. And then we go ahead and then linearize it. So we substitute, and then we realize that we end up having beta S naught of the controlled minus these terms times I. Sorry. So we expect the infection to grow only when this, which is this beta here, we know is the rate at which there is recruitment from the susceptible compartment into the infected population. And so once this is bigger than all these terms, then we expect that the infection will grow. And so obviously we see clearly that once this is greater than 1, we expect the infection to grow. And this is very similar to what we know as R naught should be greater than 1. And so this becomes our um, uh, reproduction number for the controlled system. So we see also clearly that now what we have is just an addition of new terms from our old reproduction number from the uncontrolled system, which we see as that. Now, sensitivity analysis was conducted, and then it showed that the control terms U1 and U2 are more sensitive with respect to the reproduction number. And then beta and lambda follow with phi and then mu being the least. Now we look at the objective functional, and the objective functional for minimization would have I, because we are interested in minimizing the infection. And so we have I and then U1, all depending on times, space directional X and then space the direction of Y. Same for the U2. Now our admissible control set is given by this constraint, and then it's coming from this space. Now we would need to find the smoothness constraints on the controls, and so the smoothness control is also given by these, bounded by epsilon sub 1 and then epsilon sub 2. The next is that our spatial smoothness constraints on the controls would have to also include the spatial part. What we did was for the transport, and so this would be for the spatial part, which is also bounded by kappa 1 and then kappa 2. Now we need to discretize time, so we go ahead and then use the finite difference method. So for the finite difference method, we define Tn to be this, and then x sub j to be that, and then y sub k to be that. So these are discrete state variables. And so for the time discretization, we expect that for the forward Euler scheme, we would have the partial derivative of the susceptible compartment to be of this form, approximately. And then we will repeat the same for the infected and then the recovery compartment. And this gives us the second order using the central difference. And this would be the discretization of the flux terms. The flux terms are with respect to the velocity. Same for the recovered population. And this gives us the adjoint equation. And the adjoint equation is needed for the susceptible, for the infected, and then the recovered populations. This gives us the control update and projection. So the time steps are bounded by epsilon for the control variable 1 and then the control variable 2, which is the treatment, and then the vaccination. And then the error here is with the convergence tolerance of 10 exponent 6. Now this gives us the table for our parameters. For the parameter uppercase lambda, it is estimated, and then beta and gamma are all from these papers, and then it was fitted for the velocities of the susceptible and then the infected population. So data from Nigeria was used for the fitting, and in the first, we have confirmed cases with respect to time, and then the blue we see is for the data, and then the red is for the fitted curve. Same for active cases. The red we see is for the fitted curve from the model, and then the blue is for the scatter plot of the data. And then we also have the death cases from the model is the red, and then the data gives the blue dot. Same for the recovered cases, which shows that the model fits nicely in a real time data. Now, we go through the numerical scheme and then run, and then this is what we are going to get. We see clearly that when we simulate for the time of 5 days, we see the concentration is at 0.55. There is no control measure yet. When we move from 5 days to 10 days, the yellow part, which is the concentrated area, reduces, which is 0.35. That is the susceptible population, reduces from 0.55 to 0.35. And then when we move to the 15 days, it is so clear that it has reduced to 0.26, and then it has further reduced at 25 days to 0.22, which shows that if there is no intervention, the disease would continually spread. And then the velocity field would mean that the flow of the spread in the horizontal direction in 5 days is also simulated as that. You see clearly that it is also 0.015. It reduces to 0.01 for the concentrated area for the susceptible population. But it is observed that the vertical flow is faster than the horizontal flow, which means that if there is any intervention to be used, then it should be along the vertical, not the horizontal, because it is clear that after from 15 days to 25 days, we have the susceptible concentration reducing from 10 to 6 here. Now, this is the spatial distribution under the control measure. We see clearly that when the control measure is used for the susceptible population, which is the vaccination, the concentration of the susceptible population would be within the 5 days at 1.8. It increases to 2.05, and then when we move to time again for 15 days to 25 days, we see it increasing from 2.35 to 2.4. And then it would observe that the infected population would rather be reducing to 0.4, from 2 to 0.4 as it's shown. The next is for the treatment control. For 10 days, we see clearly that the concentration of infected the concentration of susceptible increases from 5 to 12, and then it again further increases from 18 to 30.5. And so you see clearly that when the control measures are used, the propagation of the disease or the spread of the disease reduces with respect to the successful being vaccinated, and then the um, infected population also being treated. Now it is clear that along the slides, cost minimization was also included, so that the running of the scheme doesn't bring about more costs. And so these boundaries are here to ensure that the cost for the implementation of the controls is also minimized. So in conclusion, it is clear that when the ordinary differential equations are used for the understanding of the spread of the COVID-19 in mathematical sense, it is limited. It doesn't give full understanding of how the disease would spread or how fast it will spread. But with the use of the spatial model, which is taking into consideration the transport equation and then the Euler equation with inviscid flow, we tend to have a very better picture of how the disease will spread, and this will in turn help policymakers to know which direction or which trajectory that they should use to control the disease. These are some of the references used in the slide. Thank you.